Right, so, well, first of all, thank you, Ignacio and Anna, for introducing my presentation, and thanks to the organizing committee for giving us the opportunity to present our work here today. I apologize on behalf of Dr. Rongsheng Chen, who was unable to present today, and I'm the one on the right there. My name is Federico Formenti, and I'm aware that we were asked to put a photo of the first author or the presenter here on the first slide, but Rongsheng and I weren't sure whether you want to see me or him. So we thought we'd find a solution to the problem and put a photo of the whole team. So Rongsheng Chen is the one that appears on the right of the photo. He's got two main characteristics. He's a bit of a magician in making these oxygen sensors, and the second one is that you can probably see he doesn't like low-waist trousers. Then there's myself and our two supervisors, Dr. Farmery, Professor Hahn, and two of our collaborators on the left. In general terms, we're interested in translational physiology. So we are interested in the development of technology for physiological monitoring and its application to clinical settings. For example, the thing which is most relevant for the presentation today is that there's certainly a need for fast and small oxygen sensors for clinical applications. For example, the little baby there may well be in an intensive neonatal or pediatric intensive care unit. And here there would be a need for fast and small oxygen sensors to monitor their breathing, for example. Another application is the one in blood. So the first case is in the gas phase, and the second one is in liquid. In terms of an example of application, which is what we're most interested in, is monitoring the partial pressure of oxygen in arterial blood in patients who are on a mechanical ventilator because they cannot breathe on their own. And in their condition, the lung, when they breathe out, the lung or parts of the lung collapse, and that results in no gas exchange until the following breath and a consequent decrease in the partial pressure of oxygen in the arterial blood. That is restored when they breathe in or when the mechanical ventilator pushes pressure into the lung. And in this example, again, there would be an oscillation in the partial pressure of oxygen which follows the rate of breathing. So in this example, we have an application in liquid. Some of the most popular oxygen sensors are the Clark type oxygen sensors, which are electrodes. They started being used in the 50s from some pioneering work at the time. And they're the most popular ones that are used in hospitals when we're taking a blood sample, looking at gases. They most likely would be in the machine that analyzes the blood sample. For our applications, they've got a few limitations. First of all, they consume the oxygen that they're trying to measure. So if we're looking at measuring oxygen concentration at the low levels, this would probably not be an ideal solution. Because it's an electrode, it's sensitive to electromagnetic interference, which again, in an operating theater, may be better to be avoided. And it's got a relatively long response time of about 60 seconds, which appears in the diagram in the top right corner, which is from the Journal of Applied Physiology 1953 article. I know that they've made much more rapid sensors of this type in the last 10-20 years, but these remained at a prototype state. And one of the limitations generally in the field, but certainly for the Clark type electrodes, is that they accumulate blood clots on their surface. So they're prone to this clotting on the surface. So you can coat them, but the coating reduces their response time. It takes longer to get the measurement done. So for these reasons, at least, these sensors are not ideal for the clinical applications I mentioned in the previous slide. An option in this respect that's been available for quite a few years now is the use of silica fiber optic sensors, which the working principle of which is fluorescence quenching. These sensors are cheaper than the Clark type electrodes, and they're smaller, so they are usable in patients' blood vessels. They do have one limitation still, which is their fragility. So when we want to use them in a patient's blood vessel, we don't want it to break easily. And this material is not ideal in that respect. Now, a solution is to use plastic fiber optic sensors, which are less fragile. The image on the right shows you, it's just to give an idea that you can bend them quite a lot and they don't break. Their diameter is about less than 0.5 millimeters, although Rongsheng's made smaller sensors going down to 0.2 millimeters. And the dollar coin over there is not the actual price. It's cheap, but not that cheap. But it's just to give an idea of the dimension. Now, this sensor's got at least two limitations compared with the silica fiber sensors, which are reduced sensitivity and a long response time to changes in partial pressure of oxygen. So Rongsheng thought that a potential improvement was to increase the oxygen permeability of the fluorophore matrix. So in other words, the question we were trying to answer with our experiments was whether longer pendant groups in the polymer could improve sensor sensitivity and its response time. In order to do this, we tested three polymers. We've got PMMA on the left, PEMA in the middle, and PPMA on the right. And you see that with colors, I've tried to highlight that they've got different pendant groups, shorter on the left and longer on the right. And at the bottom, there's just a diagram that shows the molecular structure of the embedded fluorophore, which is platinum porphyrin. Now, for those of you like me who don't like chemistry that much, I've tried to think of an analogy that hopefully will make sense to everyone. Here on the left, we've got the short pendant group polymer represented by fine clay, and the drops of water represent oxygen. So you see that in a given unit time for, say, 7 drops of water on top of the fine clay, we only get 2 drops at the bottom. In contrast, on the right, there's a long pendant group represented by large stones. And here you see that in, assuming it's the same unit time, that more water goes through the large stones. In this respect, what the main point is that between these two materials, the difference is that there's more empty space. And so oxygen can diffuse through more rapidly in long pendant groups. At least this was the hypothesis underlying our work. So we did want to see how the different polymers affected the sensitivity and the response time of these sensors. When we wanted to measure sensor sensitivity, we used a system which was presented here, I think, about a year ago. And we have two, is there a marker? Pointer? No. On the left here, we've got the 2 gas cylinders. There's nitrogen and oxygen. And they feed through into a gas mixing pump where we can set the oxygen concentration from 0% to 100%. And then that mixed gas flows into a testing chamber where the sensor sits, and we can measure its sensitivity to changes in the partial pressure of oxygen. Here we're very lucky because at the University of Oxford we've got high technology, which is this thing here. It's got a couple of dials. It's been there for probably around 70 years or more, but it does work well. We tested it, we compared with other systems, and it is a valuable old tool. Now, the results we obtained when we did these tests are represented by this diagram here. On the horizontal axis, we've got the oxygen concentration going from 0 on the left to 100 on the right. And on the vertical axis, there's the intensity of the signal that we recorded with the 3 different polymers. And you can see that the triangles which are on the top line show results from the PPMA polymer, which showed greater sensitivity than PEMA and PMMA matrices. For example, if you look at values between 20 and 80% oxygen, you see that there's only a small increase in the PMMA results at the bottom and a much greater increase in the PPMA polymer at the top. And when we wanted then to move on measuring sensors' response time, we used, again, an apparatus that has been used before. Here we have two pressure chambers, P1 and P2, which feed gases at different pressures into a testing chamber at the bottom, and we can control the change in pressure with a switch. The sensor sits into the testing chamber, and it appears in the photo over there on the right, where we've got the two pressure chambers at the bottom, the testing chamber in the middle, and you can see the white wire, which is the oxygen sensor that goes into the testing chamber. And this system was used to generate pressure step changes that we could monitor. The results from these experiments, when we changed the pressure of oxygen from 5 to 15 kilopascals, are shown here. On the horizontal axis now we've got time, and you see that the PPMA matrix showed a faster response to the increase in the partial pressure of oxygen than the PEMA and PMMA matrices. And again, the similar results were recorded when we did the opposite, so when we went down from a pressure of 15 to a pressure of 5 kilopascals. Again, these new matrix with longer pendant groups responded more rapidly. Now, as a general conclusion, we think that then longer pendant groups in the polymer improve sensor sensitivity and response time. And as a consequence, we do believe that there is a potential interest for their clinical applications, at least in the examples I mentioned at the beginning of the presentation. Now, in terms of limitations of this sensor at the moment, they're mostly relative to the silica fiber sensors, and they're either unknown or potential. We're working on them. So we don't really know the polymer and the fluorophore shelf life and long-term utilization. We don't know about the potential signal loss in the waveguide, which may not necessarily be an issue in an operating theater where the sensor is only a couple of meters from the recording point, but it may be an issue in other applications where the sensor is much farther away. In terms of future work, we are working on a real-time temperature compensation algorithm. That is clearly because, for example, in the little baby that was shown at the beginning, there would be air going into the lung at a room temperature, and air coming out from the lung at a higher temperature, for which we need to compensate. And we're developing a multi-parameter measurement device. We need to assess the long-term stability, and that is required for the integration of oxygen sensor in a patient monitor. And we're working in collaboration, but looking for more collaboration with industrial partners for the refinement and commercialization of the sensor. I'd like to acknowledge the help and financial support of the EPSRC and the National Institute for Health Research, and Oxford Optronix, that is our collaborator. As I mentioned at the beginning, perhaps, I'm a physiologist, so I apologize in advance if I cannot answer very technical engineering questions. The best I can do is probably just give you then Rongsheng's email and contact him. More than happy to answer any questions about the applications and the use of this sensor in clinical settings and where we are at the moment. And thank you for your attention.